Go back to the thermo for me. And I am videoing for my crew. I had a couple of notes to add to either your BIP notes itself or ideas that you were writing down for yourself from your own personalized studying, because I'm trying to give you very little to do at home. 3 FRQs I just think would be like maybe 20 minutes or so, since they're like kind of short on one of them. So this might be some news to you. This might be old school because you've already done your thermal review. So I'm going to hit these pretty quickly. What do you think I mean by solution? Delta H of solution, so enthalpy of solution, can be endo or exo. The whole entire solution process. What's it depend on? Like, for example, a salt going into solution. What are the 3 steps? AJ?
Overcoming the bonds within the solute.
Okay, so overcoming the attractions of the solute, and that's probably going to be what kind of process? Endo or exo? Definitely endo, right? But there's more attraction to overcome within a compound like an ionic structure, so it's definitely endo. Next. Okay, and which is an endothermic process, and that's aqueous solution. It could also be anything non-aqueous, which would still have intermolecular forces within a solvent. So we're overcoming solute attractions, we're overcoming solvent attractions, and then what? Okay, so when the particle attractions start to occur, that's stabilizing, that's releasing energy, and so if H3, which is exothermic, is much larger than the energy it took to separate solute and solvent particles, what would the overall delta H be? Exothermic overall, and that's what we call H of solution. But what if the energy given off by H3 was just a little bit, was very little, low magnitude exothermic? The entire process would be endothermic because H1 and H2 would overcome or be larger than that value. So sometimes you'll have to itemize like individual enthalpies to look at a total enthalpy change. A lot of times they'll ask questions, and so they take pride in trying to asking you questions that are very situation or scenario based. That kind of throw you off. They're like, we dove under the ocean and we looked at this crab and it's got this thing in it we want to extract. So you get distracted by the storyline before you start looking at the chemistry. So they'll a lot of times the thermodynamic stuff comes from like extraction of metals from ores, and so they'll say, oh, an ore is 80% aluminum. This takes 100 kilojoules to extract the aluminum to make aluminum oxide. So if it starts talking about ores or anything, it's just how they reference the real world application of metallic or thermochemistry. We know this endothermic, the system versus surroundings, the system gains energy, but as it gains energy, it uses it up, right? So how does that feel if you're holding the test tube? Cold. That is, I don't know why, and it's so confusing to people that if it consumes energy, it's gone, and so there's lower energy, it's going to feel cooler. And there's some explanation behind that with the differences between potential energy and kinetic energy, but what does P mean? I wrote my little abbreviations for myself, and you see I remember what this means. Don't know what P means. I'll pass on that P for a second. I'll come back and remember what I meant by that. P. Yeah. I'm gonna go to exothermic. Okay, so you guys know your ideas, system versus surroundings. Exothermic pushes energy from the system to the surroundings, which makes the surroundings feel warmer. It is caused by a difference in potential energy. Products, yeah, that's what, oh, because I was referencing curves. I just erased all my notes from here, so referencing curves. So this is, thank you, endothermic. This is exothermic. So P as in products, thank you, will differ in potential energy, and so as you have a higher potential energy, there's an interchange of kinetic energy, so you lose the kinetic energy, you are at a colder temperature. And then vice versa, when you have lower potential energy, essentially you have a higher kinetic energy because there's an interchange there, and then as you have a higher kinetic energy, you're warmer. But there's an interchange between system and surroundings. Okay, what is specific heat capacity?
How much heat required to raise the 1 gram of the substance by 1 degree Celsius?
Okay, so one gram of substance by 1 degree Celsius. So how do we write that into a unit form?
Joules per grams times
Right, so thermochemistry, just thermochemistry is a small little bubble, it gets Celsius. But thermodynamics, which is about entropy and enthalpy and gives free energy, they have to use what unit of temperature? Kelvin. So this is where we do get to use Celsius and stick with it. And last year, maybe the year before, they did use Kelvin within thermochemistry itself. It works the same way. Don't try to convert to Celsius, just use the Kelvin they gave you. But most of the time we do have this expressed in Celsius. And this is a factor that will go into what equation? Yes, Q equals MCAT. So MC delta T, Q stands for heat, which is expressed in joules, and then M is mass, which is expressed in grams. C is specific heat capacity, T is T final minus T initial. So that is in Celsius, just as a quick reminder for those. Calorimetry is the process of actually exchanging energy with systems versus surroundings. And so the system losing it, the surroundings gaining it. We express one as positive, one as negative, which is why we get this Q is equal to Q scenario. Whenever you're labeling this, let's say you have a coffee cup calorimeter, you put some water in there, you put a hot metal in there. Hot metal's going to do what?
Heat up the water.
Heat up the water because the hot metal
Will give off heat.
loses energy, right? So I could say Q of metal, Q of metal would be the negative because it loses energy, or Q of water gains energy. But how would I measure the gaining of energy of the water? I'll have what inside? A thermometer to measure the heat exchange, because we don't have anything that measures heat. We have something that measures temperature, and we backtrack to calculating that heat. Yeah.
When you're doing calculations, do you have to do that explicitly, or can you just change the signs?
Sometimes they give you upfront credit for noticing the system and surroundings. So if you figure out that you can, then I would set it up and label which one's losing, which one's gaining. Specifically when we're doing a calorimeter, so like a calorimetry, you say Q cal equals Q solution, or Q cal is equal to whatever the reaction is. So the calorimeter's job is to absorb the energy, and so usually it's going to be asked as, let me see if I have some space here, maybe. So what if I said Q cal equals C delta T? Notice the C is capital. What does that represent? Big C. Say again? I heard somebody say it. So specific heat capacity is little c, okay? And this is just heat capacity given off, or given in different units. This is going to be in, I'm just going to put C for the calorimeter, is in joules per degree C. So when you multiply by your degree C, what do you get? Joules. Okay, so the calorimeter will usually be given a heat capacity in joules or kilojoules per degree Celsius, and then you'll backtrack to find the calorie, or the calorimeter's heat absorbed, which would be given off by the solution or reaction that's happening inside of it. This is usually a bomb calorimeter, and so the bomb calorimeter is a steel drum. That's why we utilize a different type of specific heat capacity related to that. Do you remember what work is? Bye. Hurry back. Hurry back. Bye. You're just studying volleyball. Okay. What is work? Do you remember any of this, guys? I hear something about surroundings. I pulled this up for you just in case. Okay. This is my study guide on the website. Check it out for yourself. What are you doing?
We forgot our phones.
Oh. Like a good student, forgetting their pens. Okay, so here's your work equation. Work is equal to pressure, negative pressure times change in volume. So write that down for yourself if you need it. If you're talking about work being done on a system, here's your system. Do your work on the system. What happens to volume?
Increases.
Say again? Decreases. You press on the system, so you compress the system. Compressing the system means work's being done on the system, so that's a positive work. If you allow your system to do work on the surroundings, it's expanding. And so it's pushing on the surroundings, so it's losing work, or it's losing that ability to do work, so it's going to have a negative work. So that's always referencing the system. There's one more thing I was going to show you here. Well, there's your QCAT and then Q equals MCAT, representing the differences there between C values. There's your pressure. I think that was actually it. Oh, I want to show you there's some example questions here. So if you wanted to see any differences in types of questions that could be asked, they were all here. But this is back from like when? November? October? And so if you ever see Q calorimeter, that's referencing cat, and that's the temperature change of the calorimeter. Q column means Q of combustion, so most of the time it's a bomb calorimeter. It's combusting something inside of the steel drum, and that's what's causing this energy to be exchanged. So that's what our bomb calorimeters are mainly used for, is combustion reactions. Thermochemical equations are the ones that have our reactions, balanced chemical equations written, and then on the side it says delta H. Those are the only times we can ever use whole number coefficients. We can use fractional coefficients there. Hess's law, do you remember what that is? And you cancel them out, right? And what happens if you have to flip a reaction? What do?
You multiply the delta H by negative.
Right, so you flip the sign of the delta H. So if you flip a reaction, you change the sign of delta H for a Hess's law summation steps, or Hess's law can just be summation of delta H products minus summation of delta H reactants. That's called manipulating delta H, by the way, if you're changing the sign. And oh, this was what we talked about yesterday, bond dissociation energy. That's the only time you find delta H in what way? Reactants minus products. Because simply we're saying bonds broken minus bonds formed. And why are we minusing bonds formed? What is that kind of supposed to indicate to you? So bonds broken is a what kind of process? Endothermic process, right? Karate chop. And then when you minus, you're basically expressing that as a negative because it's an exothermic process. So that's really why we do it that way, in case you're wondering. And then our thermodynamic stuff talks about entropy some more. We talked about that a little bit yesterday, but that's definitely where we use Kelvin. And there's your TOS equation, and then that's just some environmental stuff. So, okay, I feel good that we reviewed thermo decently. Okay, let's do this. Just make sure we're on the right one. What's up? What's up, Roshi?
Oh, so, at equilibrium, does delta H equals
At equilibrium, so at equilibrium, delta G is equal to what? Delta G naught or delta G? Delta G and delta G naught can equal 0 at equilibrium because there's no thermodynamically favorable process in the forward or the reverse direction at that point, because it's both rates of reactions are occurring at the same rate. Because delta G is at different standard conditions. I think I'm right there, but I might have to. That's one thing that I don't memorize and I have to go back and calculate. So these are the top of the BIP. You guys have seen that about a million times. Oh, here's your delta G. Well, this is for Neffy. Oh, I want to go over phase diagrams real fast. Let me draw it over here. What does a heat curve look like? So it's not a curve? Okay, just making sure. So you know it's a staircase. And they had this on one of the exams last year. So, what was it last year? Maybe year before. So it looks like this, right? That's assuming we're going through all phases of matter, solid, liquid, gas. Okay, but what if I said, okay, how much heat is required to melt aluminum and raise the temperature to 100 degrees Celsius? So they have to tell us the melting point of aluminum. Let's say solid aluminum's down here, it's at 20 degrees Celsius. Let's say its melting point's at 120 degrees Celsius, 220 degrees Celsius, something like that. So we start at 20, and we want to melt it, and we want to raise it to 300 Celsius. Let's call that right here. We're going from here to here. How do we calculate that heat? The heat required to do all of that. Any takers? So this is heat added, and this is temperature. Yeah.
So, like, for instance, what heat do you have in cat?
Why?
Because that's changing temperature, not to change things.
Okay, so a sloped line here has a temperature change associated with that, so that would be 200 there, right? So Q1, I'm going to call here. Q2, I'll call the middle spot, and then Q3, I'll call out here, okay? So this is MCAT. Given the fact that we probably have the mass given in this problem, we would have the C given for a solid, but it would be different than the C given for a liquid. Okay, and then we find the temperature, which we can see from the graph is 200. That's just the heat associated with heating this part, or that's just the heat associated with raising that temperature. And then Q2 would be what?
Q delta H.
Q's,
Or
say
M
it?
delta H, right?
Do you say M?
Yeah.
Do you mean moles or mass? Okay, so if the delta H was given to us in like kilojoules per gram, I could use that. But if it was given to me as kilojoules per mole, just take my mass, get to moles, and then multiply it. So I'm just going to put moles times delta H, because it actually, delta H is generally given as a kilojoule per mole situation, but it could be given as grams. So that's no temperature change, right? Because it's a flat plateau. That's where phase change is occurring. That's where melting is occurring. What do we normally call that delta H of melting?
Delta H of fusion.
Fusion, right. So have a fusion, delta H of fusion variable given to you in that problem. So that's our non-temperature change, which is why we're not using the equation with delta T in it. And then Q3, which is here, would be what? MCAT again, but the C would be slightly different because of the liquid nature. So then how would we get the total heat? Add them up. This one's probably in joules, this one's probably in kilojoules, this one's probably in joules, so we'd have to make sure those were constant before adding them up. Alright, so that's stuff you did in honors chem. We maybe did 1 or 2 back in thermochemistry, but it's when you realize that you have to use a heat curve, stop, think about the sections, do a little sketch for yourself, and then think about what equations correlate with those sections. Questions there, guys? Okay. Alright, so let's look here. Here's the one with many people had some questions on. So you have all these materials available. Someone here? Hello? Hey, Emma, what's up? Sit over here. I'll get you in a second. For a field trip. Okay. So, alright, read this for a second, guys. Because I know this was one of the ones you had issues with. Can you guys see that okay? Tell people if you're not passing a class, don't ask me to sign it. It's the rule now. We have no choice, yeah.
Jacob will be here soon.
Thank you. I don't know where he's at. Okay. So this question, what page is this in the packet?
34.
Thank you. Okay, so this is where the person had to determine if their materials would allow them to get to sig figs. And you guys had this big conversation yesterday. I was like, we'll go over it soon. So they are using the beakers, right? Okay, so why is it 50 plus or minus 10? Where does that information come from? So when you go up here, you're looking at your precision information, right? So plus or minus 10 is the least one of the least accurate ways. Because over here you get an extra sig fig as you get an extra, you get a decimal actually with it. So the graduated cylinders would be the most accurate. What's even better than a graduated cylinder? You're right, which was an option here, but we're good. All right, so you know that for sure by now. So justify, they won't have the ability to get into two significant figures because 50 to 60 or 50 to 40 is still just one sig fig in that measurement. Okay, and then enthalpy of reaction. What's enthalpy of reaction going to be measured in? Kilojoules per mole. Okay, so we're looking for kilojoules, which we get from how? Or we get from where? MCAT, and that's going to be mass times C, which is our specific heat capacity, times delta T. So delta T is where our measurement part comes in because the mass is going to come from using volumes and getting our individual volumes put into their container. And then our delta T comes from what? Where does our delta T come from? The thermometer, okay. So looking back up here just for a hot second, the thermometer gets into what? 0.1, so that's a decent amount of sig fig, so we should have some accuracy there. All right, so specifically, they could use the graduated cylinders, which allowed them to get to more accurate volume using the precision of 0.1 as an extra decimal. or the use of, I thought they said thermometer on this one. Yeah, they did, okay. So, never mind. I don't know why you couldn't use the thermometer. Maybe because we didn't really have a chance. You only have one thermometer. You had to use a single thermometer. Okay. But the other way with the molarities, you would have a greater temperature change, which getting you to a greater temperature change gives you more sig figs in general. 2 degrees Celsius, so 2.0 versus 12 degrees Celsius, 12.0, 2 versus 3. So using the solutions of higher concentration could yield higher temperature changes. Who gets this a little bit with the error analysis regarding glassware? It's not something we did a whole lot of because mainly we're looking at error on the backside of like a procedure, not really the glassware choices. But that's why I harass you guys about using beakers and or flasks, because they are not accurate at all. All right, so we'll come back there if we need to. This one had us looking at experimental calculations. So tell me what you guys did first, and then I'll scroll down.
Moles.
Found moles how?
You have volume and polarity, so you can just use them.
So M times V gives you moles, okay? And for both of them, you get the same number of moles, right? Okay, keep going.
And then you just do it gives you the kilojoules that they got.
Mm-hmm.
So then you just divide that by how many moles.
How many moles did you divide by?
0.075.
Why only one and not combined?
Because it's the delta H for one of them, not both of them.
Right, delta H, whenever you establish a balanced chemical equation, it's always referring to each of the individual reactants separately and each of the products separately. And so that's a ratio that's concerned within the mole ratios. So if you have one that was lower than the other, so that would be your limiting reagent, that would be the one that basically controls the heat evolve. So that's when you should use. But in this case, they were the same. So you're dividing by the same, or dividing by one of them because it'll end up being the same result. So there's your moles divided, or sorry, your moles divide, you're going to use them to divide by the heat evolved. Did you use a negative? Because it was exothermic. Okay, so that should, and that's the case for every single acid and base. Every strong acid and strong base really only have an NIE of H plus OH minus makes water. If you're considering them as strong acids and strong bases with H pluses and OH minuses. Literally every strong acid and strong base combination neutralization reaction has that delta H. It's kind of interesting, and so you might even notice something like that on a test. All right, so you guys see the points. Moving on. Can I move on? All right, so the next one, they assume that the thermometer and calorimeter do not observe the energy, which is not an assumption you should make. You should always assume that they're observing some energy. So what does that do to the, don't look yet, what does that do to the value of delta H? When you say lower, give me a directional, like lower exothermic value or endothermic or what? How can you explain that?
I said smaller magnitude.
Smaller magnitude exothermic reaction? Okay, so a smaller magnitude exothermic reaction is actually a larger number, right? So whenever you're saying it, pick one way and explain it like that every time so you don't get screwed up. Because when you say bigger, they don't really know if you mean bigger number, magnitude-wise, or just higher in terms of the number itself. So be very specific, and then tell us why. So you said lower than because, just by your answer.
Heat absorbed by the thermometer and calculator would be more saturation.
So it was actually more exothermic than it's read to be. Okay, so when you're saying that, try to use exothermic so that they understand you know what you're talking about there. All right, so this one's really wordy. I explained it a little bit smaller or fewer words. And this is double I. Yes? Okay. So, see how they specified lower, which is smaller, less negative? I really don't like the fact they said lower, but it is truly lower magnitude. Because you didn't take the heat into account, that would have been absorbed by the materials of the lab. So the thermometer, or the heat loss that was ignored, would have made the actual value more exothermic. So this assumption made it a lower magnitude or a less negative exothermic reaction. Kind of blending that, I think just saying less exothermic or lower magnitude exothermic reaction should kind of suffice. I don't really think anybody would have talked about the heat capacity. Did you guys talk about that? That's not something my students usually hit because this is understood, like you can figure it out. They don't absorb it, or it does absorb it, you don't account for it. You could talk about the heat capacity as well. They try to give you some options for especially air analysis because there's many things that can be assumed. But the heat capacity being excluded would show that it was more exothermic than it truly was. Okay, so we're moving on to the next one. Oh, this is the one that I was kind of just talking about. This is an acid-base, strong base reaction. So when you're talking about goes to completion, justify the validity of the assumption, assume equilibrium constant for the reaction. So if it goes to completion, first of all, what do you already know about K? K equilibrium K. It's ridiculously high, right? It's off the charts. We can't calculate it. And then if you're talking about well, I'm just going to show you guys here. The strong acid, strong base relationship. Well, we know that strong acid is H+, strong base is OH-. We know that's the formation of water. Well, if it goes to completion, we already made the assumption that K is very, very large. But if you look at it, you actually maybe notice that's the inverse of KW. That's the inverse of the autoionization of water. So if KW, which is the autoionization of water, takes water and makes ions, that's 10 to the negative 14th. When you inverse, or when you reverse an equilibrium reaction, what do you do to K? Say again? You can't flip the sign of K. There is no sign of K. Inverse the K. Remember that? So delta H, you inverse signs and manipulate by, if you multiply a reaction by half, you multiply the K, the delta H by half. This is different. K is manipulated by taking K1, and then when you reverse it, you're going to change that to 1 over K1, which is going to make that 1 times 10 to the 14th, which is ridiculously high, as Kirk said. Yeah, virtually gone to completion for most neutralizations. All right, so third student calculates the value of enthalpy that is significantly higher than accepted value. What did you guys say were some errors in the reaction mechanism made that happen? Yeah.
They could have accidentally used the 2 molar instead of 1 molar, but then calculated it as if they used 1 molar.
Okay, so using incorrect molarity would that change? So both reactants, they use the higher molarity?
Yeah.
Okay, so what would that have done?
Yeah, but then the moles that they would calculate would be less than was actually in the reaction, so it would be higher kilojoules per mole.
Okay, I can go with that. Somebody have something else? Yeah.
I said they read the thermometer in a way that like increased enthalpy.
So they wrote thermometers angle wrong.
Yeah.
Anybody else? I have a really obvious one. Oh, hey, yes. Sorry. I was expecting yours. So one more really obvious one. Coffee cup calorimeter, right? There's a lid. Most of the time we close it, most of the time. What if we don't? We left it open, and what could have happened? The heat could have escaped, and then you don't capture it, and then the thermometer doesn't read as high as it should. Therefore, your calculation is lower than it actually is. Okay, so there's some of that. Read that first, and then we'll talk more. Hi.
I have a brief.
She had some class. Oh, here you can class. Thank you.
Well, if you're saying that would lower it, but in the question it says that it was higher.
Less exothermic. Yeah, I remember the exothermic nature of that. That's why I was concerned about you saying double moles, or double moles would actually make it more, yeah, I know, but I was making sure you were thinking about more exothermic when you were talking about it. Okay, so I said the student could have allowed the heat to escape, resulting in a more endothermic cost, or in more endothermic value. This person said, talking about the thermometer being read incorrectly, so something too high or too low, mistakenly putting the 2 molar in, and that actually went along with part II. So you couldn't use incorrect calculations. Yeah.
For something like the thermometer thing, that's basically linear. So if you as long as you like actually specify it, it's okay.
I think that's okay, because I wouldn't have said thermometer error, because I think that's human error. And, but if you said they read a temperature too high or too low, I guess they give you credit. They gave like 4 or 5 options on this one. When I have another key that has what they actually gave credit for, because sometimes they modify it afterwards based on people's responses. All right, so then based on that identification of the error, you are then to find, explain how the error, I didn't highlight this, explain how it is calculating a value that is too high. So there's your information, which is delta H, which is just Q over moles. Q is our heat. So if Q is our heat, it's mass, it's MCAT. So if your delta T was high, it would have yielded a more exothermic reaction. Or if you changed it to say read it too low, then it would be a more endothermic reaction. I look back and see how the question was phrased. But if the measurement basically could be related back to delta T or to a massive solution by using higher molarities, then you should be able to get your points there. That was definitely the most lab-based question that they usually will give people. Something like that, or with gases with like UV tubes. They like to do thermo though, or stoichiometry, like gravimetric analysis, where you get a filter and you mass out a compound and you precipitate it and you filter it through. They'll do some mass differences there, and then like do percent yield, percent purity, things like that. So it's very lab-based. All right, so I'm gonna pause for a minute because you guys are slightly dead. You guys want to continue checking at thermo, or do you want to do some equilibrium? You can't say nothing. Finish this? Okay. So this is the one that required you to take into delta G thermodynamic data. Okay. Okay. So calculate delta G. How do you calculate delta G given these? Products minus reactants, right? So you have 2 of the products, water, and you have 1 of the calcium sulfate products minus calcium sulfate. What do you call this? Calcium sulfate dihydrate. Okay, so minus 1 of those. So just make sure you're using your coefficients there and you're good. What'd you guys get? What'd you guys get? Negative what? Oh, I didn't get negative, sorry. 18.22? Okay, kilojoules per mole. Alright, so that's just making sure that you're doing products minus reactants. 1 point for the setup with your ratio. See, 1 point for mole factor of water. And your final answer. And then how would you get... I'm trying not to show the answers immediately. Alright, so how would you get delta S given data for delta G and delta H? Toss. So delta G is equal to delta H minus T delta S. So plugging in your variables, the only thing you need to make sure is that you are in Kelvin, which is 298 Kelvin. Kilojoules and kilojoules will work out. But as you calculate and you do delta G is equal to delta H minus T delta S, and you plug in those values, many times our final delta S value is in joules, because you see that 0.29. They would give that to you as in kilojoules per mole Kelvin, because the Kelvin doesn't cancel out. But many times delta S is just naturally expressed in joules per mole K because it's a smaller value. So 1 point for substitution with units, and then correct answer with units. Yeah.
So is there like certain questions where you have to do simple schedule next one, or is it like
So across the board, 100% you should do correct units and correct sigfigs, because why would you not, right? Because you're a perfect student, okay? But they take one question, and they don't tell us which one it is. One question is the one they grade really harshly on units and sigfigs. Actually, no, they probably grade harshly on units across the board, because if it says to include units and you don't, then you're done. But like, let's say you put 3 sigfigs on a problem, it should have been 4. Your answer may be right, but you will not get that point of credit because your sigfigs were wrong. It's usually the biggest lab-based question that they have, because that's where we have to be most cautious of our sigfigs. Okay. All right. So then, how did you guys draw nitrogen? How did you draw N2? So again, N bond to 2, N with a triple bond, and yeah, a lone pair on each side, because they both have octet. And then how did you draw ammonia? One lone pair of nitrogen and 3 hydrogen ligands. Hey guys, we're going over homework still. Okay, so 1 point for each of the correct Lewis dots. If you did not draw the lone pair, no credit. Period. And then how would you calculate Ah! There's our structures. Okay. So calculate delta G. When 12 grams of hydrogen reacts with excess nitrogen according to the reaction here, how would you calculate delta G there? Sorry. Ooh, I'm trying not to show you this. Okay. When 12 grams of hydrogen react, how would you calculate delta G?
On the moles of hydrogen,
And?
using a like molar ratio,
Okay, so moles of hydrogen, and what mole to mole ratio are you speaking of?
3 moles of hydrogen to 1 mole reaction.
Or I wouldn't even say one mole reaction. I'd just go straight to delta G. Right? Because whenever you have a thermodynamic situation. Oh, and then if you guys have cans, aluminum cans, please bring cans tomorrow. We're doing roast can honors, and I'm about out. So 12 grams of hydrogen converts to what? Give me the moles, but what's the?
2 grams.
2 grams.
And I'm just going to do something. Okay? And because anything that's thermodynamically given here, this is related to 1 mole of nitrogen, to 3 moles of hydrogen, and to 2 moles of ammonia separately. You can use them as a relationship. So what's your next step? What goes on top?
Negative 34.
And that's per 1 or 3 moles of hydrogen. And the 3 moles of hydrogen is coming from the balanced chemical equation. So I think this process of stoichiometry is the easiest if you consider it like that. And then that's what you guys see here. Grams to moles, and then 3 moles of hydrogen are related to 34 kilojoules. And that's going to be a negative. That negative does pop over here. Negative 68 kilojoules is going to be the free energy related to that much hydrogen gas being present for that given reaction. Okay? Okay. And then if you're telling me things that are exactly on the key, and we never do it that way, I don't know how you guys are, I don't really know. I'll go ahead and say this. Who sits in front of the computer and does their FRQs? Who just does them and just goes with whatever their answers are and just says, we'll check it in class? Like, do you guys check your answers online? You guys look, I mean, because, I mean, if we were checking in class and, you know, if you want that immediate gratification, go for it, but then it's useless for me to go over this in class. I could use your time differently, so let me know if this review is working for you or not. All right, so let's finish up thermo. Given this delta H, negative 92.2 kilojoules, which is larger, the total bond association energy of reactants or products? You guys tell me. Why products? Because, so the process of forming reactants is?
It's more energy to, you release more energy to make products.
Okay, so due to the negative delta H of the reaction, it shows that more energy was released due to product formation than consumed in reactant bond breaking. Yes, yes? Okay, so that's something like that will work. What's up?
So, what are some other points if you mentioned like the equation for the bond association?
Yeah, see, right here. Yep, definitely reference. I mean, if you want to reference that as they love seeing diagrams. If there's a simple diagram or equation you can use to explain, because it shows your mathematical, like quantitative and qualitative reasoning together. So it's okay to do both. But yeah, the verbalizing method of that though is it must be total more exothermic than endothermic, which is the bond forming versus bond breaking. So if you only do the mathematical, you don't have the it says explain. Since you don't have values, as long as you put some value, like fake values in, like this must be larger than this one, and then go, this is due to the more exothermic process, making it overall exothermic, something like that could work. So don't only put the equation, explain it too, okay? All right, last bit here. You have your delta S given reaction delta S for the entire reaction is negative 199 joules per mole K. Why overall is this value negative? What does a negative delta S mean? Decrease what? Over the course of the forward reaction, right? Can delta S formation itself be negative? Like 1 delta S. What do I mean by that? I mean, how do we normally get delta S value? delta S reaction. What's one way? So delta S, a reaction, can be summation of delta S of delta S of formation values of the products minus summation of delta S of formation values of the reactants, right? So this is just the difference in entropy or disordered products versus the difference in energy of the reactants to give us our total delta S. We could also do delta H, or delta G is equal to delta H minus T delta S. So this value can be negative, right? Because I can have an increase or I can have a decrease of disorder across the reaction. But can these values be negative? Delta S of formation. What law? Do you guys remember the third law of thermodynamics? Third law of thermodynamics. Entropy of the entropy of the, I think that's the second actually. Okay, so entropy of the universe is always increasing. That is a true statement. But what has an entropy of 0? Perfect crystalline structure, right? At 0 degrees Kelvin, or 0 Kelvin, because it's not moving. There is no disorder for a non-moving particle. So everything is greater than 1, or greater than 0. So just make sure that, yes, a full reaction can decrease in disorder, have a negative delta H, or delta S, but individual particles cannot. They can't be lower than 0. Okay, so when you plug that in, actually when you think about it, where's this reaction? Up here? Why is this a decrease in disorder?
Going from 4 moles of gas to 2.
Right, and so that's basically all you need to say. But elaborate a little bit more in terms of like 4 moles of gas has more disorder, positional entropy, and then 2 moles of gas has, 4 moles of gas has more disorder, more positional entropy, 2 moles of gas has less disorder, less positional entropy. I don't know, they say microstates. Microstates is a term that actually means positional entropy, and positional entropy just means positions it can take. Statistically relevant would mean if you have more particles, you can have more statistical positions. And 1 point just for your explanation. All right.
Since you mentioned positional entropy more,
I would just say 4 moles of gas have higher disorder, but due to their higher number of states they can take, they call it microstates, but positional entropy is how you can refer to them as well. You can, because you can have more moles of liquid having more positions, because it's basically like liquid particle 1, liquid particle 2, or liquid particle 1, liquid particle 2, or liquid particle 1, particle 2. So they can take on all these different positional arrangements, which give them more disorder, or more possibilities for disorder. All right, so how do you solve the last one here? So explain why there's a temperature, why there is a temperature above 298, which is the algebraic sign, that delta G changes. So you're talking about this, they're independent. How did you guys start to pull these two parts together? I think this is one of people left blank. Yeah? No? So, this 2000. Did I finish the... Oh yeah, that's 290. Sorry, I'm looking at the wrong one. Thanks, Caleb. We'll just take reaction stoichiometry, limiting reagent, reaction prediction. How do chlorates decompose? Crap. They have an AP exam in 3 weeks. How do chlorates decompose? Metal chlorates. Aluminum chlorate. Aluminum ox? No, because that'll make chlorine gas and it would kill us all. Okay. You guys are really impressing me. Anybody? It's not chlorine gas, so what is the other gas that could be produced? Oxygen gas, okay, so then what's left? Well, what's the metal? Aluminum chloride, okay. Going back, what was the one on this one? It wasn't aluminum, was it? No, aluminum carbonate. How does aluminum carbonate decompose? Say it again?
Aluminum oxide and CO2.
Thank you, Kurt. You're saved the class. Thank you. All right, you can put it up here, Marie. Okay, guys, we're gonna finish this right now because you guys are dead to the world. Okay, so I explained it by thinking about how delta H, delta G, and TOS relate to each other. How does delta G become negative in that equation? TOS is greater than delta H. So if this value is bigger than delta H, it becomes negative. Yes, yes? Okay. So that's one way to explain it. The other way, because this temperature is greater, it's going to create this term, it'll become larger, the magnitude will become larger, which would supersede that and make it negative overall. You guys can tell me this last part before I show you. So according to Le Chatelier's, how can I force the formation of more ammonia according to that reaction above? Can you know? You good? Okay. Raphael? Because it was 3 moles of, what's that? Lime. Great. How can I force the formation of ammonia? Increase what? Increase hydrogen gas or increase nitrogen gas or remove ammonia or
Increase pressure.
if I increase pressure, that's what I was looking for. If I increase pressure, this is according to Le Chatelier's, which side should be favored? Why?
Because there are more interactions between the reactants.
So the 3 to 1, so 4 moles of gas in a high pressure situation are already they're going to exacerbate the stress, right? They're going to cause more pressure, and we already have a high pressure situation. We don't want more pressure. So it's going to force the formation of 2 moles of gas, which will have lower collisions with continuum wall, which would relieve the pressure, and we're back to equilibrium state. What if I told you this was an exothermic process? So exothermic heat or kilojoules are being released. How could I then also force the formation of ammonia? Decrease the temperature, so keep it at a low temperature, and so the forward reaction would be occurring basically faster, because this doesn't require extra energy to occur, but the reverse reaction does, as you can see from the process of ammonia gaining energy to force the reverse. So if you lower the temperature, the forward reaction occurs at a higher rate than the reverse, so that's why it shifts right. Now this question was, similar but not the same. How can you increase the yield assuming high pressure and low temperatures? So that kind of explains via Le Chat's. Okay, is this it? No, there's more. All right, so you guys can see the verbiage there to see how to allow correct usage of terms. I like the fact they say drives reaction, because it says it forces it in forward direction, but in a shorter sentence. So decreasing the temperature drives reaction in forward direction, thus making more ammonia, or higher pressures achieved by decreasing the volume of the container, which is what high pressure does, should be favored, or should favor the formation of fewer moles of gas or particles of gas. Okay, we're done. You done? I'm done. I feel like I've been talking the entire class period. You have 30 minutes, work on FRQs from equilibrium. Or sit and review equilibrium in terms of like a review book, because equilibrium is a big topic. You got KSP, shots, KPs, KCs, KAs, KEs, buffers. It's huge. So either work on equilibrium FRQs or work on the review book. I have Emma's I can offer up for a little bit. So where is it? I think Jacob Brown's over there someplace. I have a Princeton review book. I like brands which is bigger.
And some cool colors.
It's,
All these FRQs?
no, I'll tell you. Let me take a break for a little bit, and I'll tell you some I want you to have done. But this is also really good. It's very short though. But it's Crash Course. It's by Adrian Dingle, my least favorite author. Dingle. I usually don't make fun of people. You guys remember Mr. Boring?
What?
You remember Mr. Boring?
Yeah.
I hated that for him. Because he endured the boring.
Galvin?
Fine.
What do you want?
Fine.
Oh, Okay, so do something. Relate it to equilibrium. This is if you haven't looked, please don't write in it. And these are my flashcards. That's Jacob's, okay? To make sure it goes back over there. Landon, you'll have to call it back to me. You're a senior.
I thought I hauled it around, put it on the side and scraped the shit.
You guys, review or do FRQs? Where you at, man?
It looks like you say you're a big car today. He does look like it.
You guys made me proud? 5?
What?
Doing you a 5 on AP exam?
I already told you I'm getting a 3.
You're getting a 6.
3.
Make them increase the scores.
I'll get you a 7.
I will raise you an 8.
So Alvin, walk out of the classroom.
Oh my god, I take a walk. That was so y'all can hear what she said. Oh my god, that was so funny.
I'll raise you an 8.
I don't get it.
She said me a 6, because I think you a 7, and she said I'll raise you an 8, and Alvin died.
I've never heard that before for one.
You never heard
They don't.
They're like a town, it's the fire. Why don't you tell her in there? Answer this for determination. Instructing.
Oh, I wasn't here.
How much is it left?
So bad.
Yeah, it's just. Oh, now it's that.
She said she wants to leave by Wednesday. That's not gonna happen.
No, that's not happening. I wish it was.
It wouldn't be fun to do.
I know.
What? What's going on? Oh, okay.
Why are you trusting Sean with this?
Yeah, I need to see Drake's gonna take the chapter.
She calls me a girl. Are you talking about that guy yesterday? I added them when I added them, it said lessons 4 minutes. All things that help. Yeah, it's actually not
No, we have a week. With spring break, a week of school, and then I think.
I call dibs on it.
It's a trap. Yeah, you like you like Star Wars? I like the shirt blade.
On my pen.
That's why I thought it was the idea. Initially. Oh, that I stopped so much. I used to think it was super hard. At the beginning of the year, trying it again the other day. They told me to do it. And then I just remember how to do it. But BDAs, I used to hate those. They didn't light up. You're learning how to organize your Cake?
Not for you, Sean. Like so.
Sean watched
Sean barely watched the class.
I was lazy being everyone's recommending.
Touch a lightsaber being fine with it? Oh.
Wait. The other side only gonna work.
Asian the one.
Reliable? You really what? Oh yeah,
So you guys are like femograph.
Hey, congrats.
I don't know where.
Okie dokie. Yeah.
Sorry about that.
If you're starting on FRQs, you should start the first one. If you're starting on just review because you're like, oh my gosh, I forgot so much equilibrium.
We say what you get.
Just, yeah, very close to you.
So who's not going to be here tomorrow?
For what?
Leadership. So some people have leadership. And then somebody have who's in the Chinese dance? Chinese dance gala.
I'm doing that.
Chinese dance gala. You're not gonna get any cake. So you're gonna, is anybody in Chinese? Mm-hmm. Never mind. That's what I'm gonna ask you guys. Come on. Did you just say do nothing?
No, I said we're not doing it.
Still, before AP exams, that's not how this girl rolls. So, either raise your hand. Either I can review and keep doing some equilibrium stuff, equilibrium FRQs, check over the multiple choice, kind of wrap up all basic review tomorrow, or we can take a multiple choice practice test and then do our equilibrium review on the day we get back on Monday. Everything. Like a legit AP exam, multiple choice practice test. Well, see, that's the thing. So the thought behind this, the reason I'm even asking you guys this question is, listen, equilibrium is a very large topic, right? I can either give it all to you as a quick review tomorrow and then let it absorb over the week and a half or so of spring break. And then you, of course, pick up some more studying here and there on things that you feel deficient in. And then practice tests, like we'll probably take 2 practice tests the week we get back. Multiple choice free response, Monday, Tuesday. Check, Wednesday. Thursday, maybe 1 more multiple choice practice. And then Friday is that 5-minute film festival. We're doing the whole day. So like we literally have no time when we get back. You think we have a week? We don't. It doesn't really feel like a week because we're going to be taking an entire class period for a practice test. But because I know you won't sit at home and go, okay, no cell phone. Let me put my timer on, hour and a half. Let me take my multiple choice by myself. Okay, my time's up. Let me check it now. There's no way you're going to do that at
I'll
home.
do that.
Yeah? Who's going to do that at home?
I'll do that.
I do that in my.
Okay, I am sorry I belittled you and your optimism.
That was understandable.
So, because most of my students would not do that. So that's why I said I would force you to do it like in a testing situation in my classroom. The logic was though is that if you're not going to be here tomorrow, I would do the practice test, which is much easier to make up than me going over equilibrium. So that's the only reason I opted to ask, because I have, who's going to leadership tomorrow? 1, 2, 3, 4. So that's a quarter of the class-ish. So you guys tell me equilibrium review and then practice test Monday or practice test tomorrow. So option 1, equilibrium review tomorrow, practice test on Monday. So that's what I'm asking right now. 1, 2, 3 is equilibrium review tomorrow. Okay, back up. Who wants to do equilibrium on the Monday we get back and take our practice test tomorrow?
We're not.
Yeah.
Yes, but that means that you'll make up a practice test, not equilibrium review.
I really meant it.
Yeah.
That's what I assumed. Okay, so it seemed like majority ruled. I will do a multiple choice practice tomorrow. It will take the entire class. Please bring a snack or 4, because you will not be talking. You'll just be thinking and noshing. And if you're not here tomorrow, you will take your multiple choice practice the day you get back, which means you miss the equilibrium review.
We'll take it as home, sitting down with the time.
I did. You don't ask me. What if we're not here tomorrow? So I'm going to just go ahead and give it to you guys to think about for 5 or 10 more minutes, and I'll get a response from you at the end. Okay? Let's do it that way. So I'll write the options on the board. And if you don't care, I just won't count your response. You just are not in the survey.
Okay, and then we might go back to option 1.
So,
And then are we gonna review it like a week before either way?
what equilibrium?
I like questions.
I will be reviewing, yeah, the multiple choice, I'm going to give you the Scantron back, we'll go really fast through it, but the free response will take more time to review because we'll be grading it. We're going to be reviewing both our practice tests no matter what. It's just, I need to know, am I doing equilibrium big review tomorrow with you guys or on Monday? That's all I need to know. And you're going to write on the card because I'm tired of asking it out loud now.
Is this the one where we have like 3 chances for?
Huh?
Is this the one where we have like 3 chances for?
We're not gonna get 3 in. Probably only get 2 in.
So this is
But
the
yeah.
graded one?
Yeah, I'm grading it for sure.
Shoot.
Like 4 grade, that's the one.
Oh, you're going
Guys, it really doesn't matter. You're gonna do it either way. It's just when do you want to do it. I give you the next card. That's all I want you to write on. Which one? I'm glad you guys were really productive the last time. Democracy majority rules.
Well, I'm not gonna lie. Oh yeah, it doesn't affect me. I'm just thinking like, if I would take
Don't let somebody influence your decision.
like, I'd rather take it before the so I would do like this, or at least I think it would, but not in the last
That practice test is graded. Yes, you are ultimately responsible for knowledge at this point. Don't you try to convince people.
The high one's gonna pass you grade, right?
Yeah, but if I only get what if I only get 2? If I get 2 multiple choice. Yeah. Okay. Pause. Shh. My goal is to get 2 practice tests in. I was gonna try to do 3, but I don't think we're gonna have time. I will take the higher multiple choice piece that I give you, and I'll take the higher free response. If I only get 1 free response in, that's the free response grade you get. But I know for sure I can get 2 multiple choice in. Those are quicker. Free response takes more of the class period. So. But yes, it is for grade initially. We're gonna initially do all of those.
I was just thinking whether or not, like,
Guys, it's not a debate. Just pick one. Jeez Louise. I thought I would give you power, but now you're just wasting class time. You get no power. After like a minute, you get no more power after a minute.